So in this project, we're going to be talking about conic sections. In particular, we're going to talk about radial reflections and the properties of ellipses. I am Christina Lulo, and
I am Clarence Grant.
okay. So before we get started talking about ellipses, we're going to first talk about types of conics. So conic sections are planes. They're cut at varied angles from a cone, and the shapes vary according to the angle at which it is cut from the cone. So there are 4 types of conics, and we've talked about these conics within this course. The first one is circles, then ellipse, parabolas, and hyperbolas. We have talked about the distinguished properties of each type of conic within this course, and we're going to elaborate more on ellipse. So each conic has a focus, a directrix, and eccentricity, in which a conic can be defined by using the focus and a directrix, as well as you can define a conic by eccentricity. The eccentricity is the distance from any point on the conic section to its focus, and it's divided by the perpendicular distance from that point to the nearest directrix. And we are going to see a visual on how eccentricity actually works. So the general equation for all conics is listed below. And the cool thing about that is that you can use that general equation and derive each equation for each type of conic, which we discovered that within our assignments for this course. So a little real world context. These conics can be seen in pretty much anywhere in life. So for example, parabolas can be seen with the sense of gravity, such as throwing a ball, a water fountain that shoots up in the air will come down. Most people have the saying that says, what goes up must come down, and that has a lot to do with gravity, which creates a parabolic shape. You can also see parabolas within architecture, such as the Gateway Arch in St. Louis or the Arc de Triomphe, as well as in things like headlights for cars. So hyperbolic paths are also formed within space, such as comets. Comets speed past the sun, where the sun is the focus. Lastly, or second to last, circles can be found in a lot of objects that we create, such as Ferris wheels, tires, coins. A lot of mirrors or bottle caps can also be used to discuss circles in our real life. So lastly, ellipses are found in everything from discussing atoms, such as the way electrons move around atoms, to how planets revolve around a star, or such as in our solar system, the sun. They can also be used within medicinal purposes, such as treating kidney stones. They actually use an ultrasound transmitter and an elliptic reflector that pinpoints kidney stones without having to do any surgical operation. So ellipses have a cool reflective property that allows us to treat kidney stones medically or without surgical needs. So we'll discuss a little bit more about eccentricity later, but as an introduction, eccentricity is basically how far a shape can stretch, such as if the eccentricity is 0, we'll see a circle. And in this GeoGebra illustration, as the eccentricity goes down to 0, you actually see the circle. If the eccentricity is between 0 and 1, the conic will be an ellipse. And if the eccentricity is more than 1, we get a parabola. The last one that is actually not showed within this illustration is that if the eccentricity is greater than 1, then the conic will actually be a hyperbola.
Now, let's focus on multiple definitions and construction of ellipses. Stretching a circle. Stretch out a circle in one dimension by multiplying the x coordinates by some factor. Let's say 2x or 3x. If you use a thumbtack construction, all you have to do is to loop a string around 2 thumbtacks and a piece of paper. You pull it taut with a pencil and trace around. Or you can slice a cone. Slicing a cone at an angle smaller than the slope of the cone itself. In other words, slicing a cone diagonally. You know, a cone is a 3-dimensional shape. It will produce an ellipse, which is a 2-dimensional shape. This is what we call cross-section. Cross-section is the process of cutting 3-dimensional shapes into 2-dimensional shapes. And ellipses range from a perfect circle, like Christina just showed, to something infinitely stretched, which can also be quantified, and we call it eccentricity. Numbers range from 0.0 to 0.99. As you just learned, a circle has eccentricity 0, and the most squished ellipse has eccentricity close to 0.99. Now, with regard to real-world situations, we got some of the example of some of the planets. We have Mercury that has eccentricity 0.206, which is not far from being a circle. Venus, which is very close to being a circle if we are focusing on the ship. And if we're looking at our planet Earth, the eccentricity is 0.017. So the Earth is like a circle, very close to being a circle. And let's see if we can look at one example of eccentricity.
I'm going to move the slide.
Christina, I think that I need to share my screen.
Okay.
So I can show some of the examples, real world situations of conics and the relationship between conics and eccentricity. Really, see if I can do that. Can you see my screen now?
Yes, I can.
Okay, great, perfect. Now let's see how that really works. we open this, you can see really what we call orbital eccentricity. As you can see here, these are the points, orbits, orbital eccentricity. You can see the red circle, it's like close to being a circle. Its eccentricity is almost zero. Compared to the purple shape, which is like it's really stretched, like squished. This eccentricity is close to 1. So you can see here there's a big difference between the shape of the red circle and the shape of the pink circle. And the reason why is because of their eccentricities. Now, let's go back to the presentation. If we also look at the solar system, which is another example of eccentricity, the sun, which is the star that the Earth orbits, and the Earth really has an eccentricity, like we said earlier, of almost 0. We are going to discuss this a little bit further in more details, so we can get our point across with it. Now, how to determine eccentricity? Remember earlier, if we use a thumbtack construction, the eccentricity is determined by how far apart the two thumbtacks are. If we stretch a circle to find the eccentricity, we divide the distance between the foci and the longest axis of the ellipse. If we're slicing a cone, the eccentricity, can be determined by the slope of the plane. Now, let's look at some of the examples in GeoGebra. Let's demonstrate that. When we were talking about the foci, it's F1 and F2. These are the two foci. And we have the blue circle, which is the ellipse. That's perfect circle because eccentricity is not 0. And P is a point on the circle. Now, the relationship between these two foci is the distances between from F1 to P and F2 to P. Regardless of the position of P on the ellipse, the distance, the total will always be constant. Let's demonstrate that. We see here from F1 to P, the distance is 5.04, and the distance from F2 to P is 2.96. If you add them up, the total is going to be 8. Now, if we move point P to any other places in the circle, we would expect to get the same value. It doesn't matter the position of P on the ellipse. Let's try that. We start for a moment. You can see here, the distance from F1 now to FP is 2.7, and the distance from F2 to P is 5.3. If we add them up, the total will still be 8. Let's try it one more time. We stop. The distance between F1 and P is 2.46, and the distance between F2 and P, which is 5.54. And if you add these two up, the total is also going to be 8. We can try this again and again and again. The distance will always going to be 8. When you add them up, the total, so because it is constant, the total will always be 8. Now let's see one application of this. If you look at the picture on the right screen where you have the sun, which is, I would say, at the center of our galaxy. All planets move in elliptical orbits with the sun at one focus. Now, if the sun is one focus, you can see the Earth's orbit is away from the sun. Now, here's one application. Regardless of the position of Earth, Earth orbits the sun, which we know it takes 365 days to go around the sun, it will keep the same distance. So now the scary proposition with that, what if one day the Earth changes orbits? It's not on that orbit anymore. So that would be a problem. This is really a real world situation. It's not just for the Earth. This also true for all of the other planets, about 8 of them that orbit the sun. Now, one thing that I've been thinking about when I started this project, doing some research, and I wonder, because I know that we're not, there are a couple of really things, theories about the universe. Is it expanding or contracting? If the universe is expanding or contracting, what are the implications for Earth's orbit? Is it possible one day Earth gets closer to the sun? What are the implications? Or Earth moves away from the sun? Because as we see in the GeoGebra demonstration, because the sun is focused, doesn't really matter. The distance should always be it's always be constant. That's if you replace point P with Earth. Let's assume that this is Earth at point P. So in that case, if Earth does not orbit the sun anymore, or does not at this point, what are the implications? What's going to happen to our planet? Again, this is also true for not just for Earth, it is also true for the other planets. Now, there's one other thing that topic that we plan on discussing based on our research is mathematical evidence of reflective property of ellipses as rays emerge from one focus past the other focus. Let's look at some experimental feats first. If you place a ball at point A, which is one of the foci, B is one, A is also the other focus. If you shoot the ball, you take a ball, you shoot it from point B at any direction, doesn't really matter where on the ellipse, you just shoot it, it will bounce off the edge. It's because it's the tangent line, the green line of the ellipse to the other focus. It's going to bounce back, bounce off the edge. of the ellipse to the other focus. And you can try that several times. You are going to get the same result. Now we need to prove that point B prime, and C are collinear. Let's see if we can prove that. Now, to prove that, it is very important to focus on proof by contradiction. What do I mean by that? So I'm going to take something that is impossible to prove, and I'm going to try to prove it to be correct. Then at the end, if it is correct, then our statement does not stand. If it is incorrect, then we have the proof that we needed. Suppose that AB prime, you see the AB prime intersects the tangent line at some other point, let's say C prime. And we assume that they are not collinear. That's the assumption, proving by contradiction. We're going to find the reason why this is impossible, because obviously we see now, if you look at A, C prime, B prime, this points on line. We're going to try to prove that it's not the case, proof by contradiction. If AC prime plus C prime B prime is less than B prime C plus CA, and if AC prime plus C prime B prime is less than AC plus CB. Triangle inequality method. Let's review this very quickly. We know that AB prime is less than B prime C plus AC. And we also know that AC prime plus C prime B prime is less than B prime C plus CA. Notice that the purple lengths are equal because B prime is the mirror image of B, since there is a symmetrical relationship on either side of the green line. Therefore, we can conclude that C prime B prime can be replaced by C prime B and CB prime by CB, resulting in a new inequality AC prime plus C prime B is less than AC plus CB. Now we also know that a property of an ellipse with respect to its foci, that CA, one of the lengths, plus CB equals to A, is constant, as we saw earlier with the planet Earth and with the demonstration from GeoGebra. Therefore, FA plus FB will be greater than A, 2A actually, sorry about that. Now, let's continue with the proof by contradiction. Let's back to the tangent line, the green line. Notice that C prime, if you zoom in, you can see actually C prime is not actually on the green line. The green line is a tangent line that intersects the ellipse once. It cannot intersect the ellipse twice at just one point, which is C. In consequence, C prime A plus CB prime have to be greater than 2A, and CA plus CB equals to A. So now we know CA prime plus CB prime must be greater than AC plus CB. thus the contradiction to our statement from the beginning, because A, C, and B prime are not collinear. Since A, C, B prime are collinear, lies on the reflection of the line BC. Having said that, any object that is sent from B, from one of the foci, will bounce off the edge of the ellipse and end up at point A, which is the other focus.
So Clarence just talked about how the distance between the foci to a point on the ellipse to the same point on the ellipse will always be equal to 2a. And we can use that to discuss how to find the standard form equation of an ellipse. So we can use the distance formula. The distance from one foci to P, as well as the distance of the second foci to P, which would be equal to 2a. If we were to write that out in radical form, we can simplify the expression and move the radicals. When we do that, we can square both sides. When you expand the squares, that would allow us to combine some terms that would lead to isolating the radical. If we were to simplify and divide out those 4s, we can square both sides and we would end up getting this long equation. If we were to expand the squares and distribute, we will be able to rewrite it in such a way that we can factor common terms. When we do that, we can set b squared equal to a squared minus c squared. And if we were to divide by a squared times b squared on both sides, we would end up getting that standard form equation that is typically taught within geometry and algebra courses. The last GeoGebra illustration is very similar to what we saw earlier, but I'm going to explain a little bit how it is used within the real life in terms of sound. So there are several examples of how this radial reflection is used within the real world in the sense of architecture. So there are several places that are called whispering galleries. If you have never heard of that, it is actually an elliptical structure where they put these plaques on the ground and they tell you to stand there. So the whispering gallery is when you stand on the foci or that plaque within the structure and another person is standing on the other foci, you can actually whisper something or normally say any sentence, and the person on the other foci can actually hear you. So as Clarence was saying, you can have the sum of both foci to that point P on the ellipse in any ellipse. Doesn't matter if A is changed or B is changed, and the sum will always be the same. Now with radial reflection, you will have something like this, where the sum will always add up to that constant like Clarence was talking about. And if someone was standing, let's say on F2 and said something while they were in a place such as St. Paul's Cathedral in London or the statutory capital in the US here, if you were to stand on that foci and whisper something, Let's pause it here. On that F2, that person who says something, it will eventually bounce off of that point P and return all the way to F1, which is actually kind of cool because in the St. Paul's Cathedral, if you have ever been there, it is a massive building. So if you are saying something normally, you would not expect someone on the other side of the room to hear a word that you have said, which they actually can if you stand on the placards that are on the ground. Is there anything else that you would like to add? Clarence?
Yes, Christina, I think you're right on point with regard to all of the great examples that you provided. Really real world examples of really the application of ellipse and the foci and the eccentricity, which I think was great.
And it also supports your explanation on the proof by contradiction.
Yes, yes, absolutely, absolutely. So these are the things that if it's good to know the real world applications because it really makes the subject more interesting.
Especially if we were to teach this to such as like high schoolers or middle schoolers, they would typically not grasp that algebraic explanation or geometrical proof. Whereas in here, we get to see the visual of GeoGebra and the illustrations, as well as where the real world context comes into play. I remember when I was in middle school, we took a trip to the statutory building or the Capitol building. And that was one of the coolest things that we got to do was stand on the plaque and say something and see if the other person could hear it. So one cool thing that I found while researching the reflective properties of ellipses was this cool experiment that this teacher had done with their students. And it was all about designing or engineering an elliptical pool table such that when you hit the ball from one focal point, it will always end up in the hole, which is the second focal point. So in this video, they actually use some creativity on how to experiment using ellipses. It did not only have to do with sound or light, but in this case, how gravity will work. And this also has a lot to do with the engineering of pool tables in general. So what they started out doing in the beginning was creating an ellipse. They found what A was, they found the distance from one foci to the other. They found the distance between the foci and a point on the ellipse. And they started to create it. They used cardboard, pencils, glue guns. Those look like a half cut open pool noodle. So what they did was they put it together using tape, glue, whatever they could find. Obviously, the tape didn't work in this case. So they'll put the elliptical cardboard into this shape and ensure that the focal point will be cut out and used as the hole for the ball to go into. So when they put all this together, we've got to stabilize it a little bit and make sure that the edges are in an ellipse form. I know this may not seem as sturdy or as precise as we would normally like things as mathematicians or scientists or even just perfectionists. But in this case, they actually did a pretty good job, and we'll see that in the end. They are now cutting a hole in the felt at one of the focal points so that the ball will have a place to go in when they hit it. Make sure that the marble can go through. This would actually be a really cool idea for students in physics, because a lot of physics has to do with reaction versus reaction. In this case, they are hitting the ball at the focal point, and there it goes into the other focal point.
Interesting.
All right. Well, I think
One thing that I would like to, even for my students, even we don't go into details, is to really show them that the position of the Earth, our planet, compared to, because they know that the Earth orbits the sun, and it is in the ellipse. Earth moves around. This is something that's been going on for what, billion of years. It's the same thing. The Earth doesn't know, like what we call a year, 365 days. Then Earth doesn't know that. We stop counting and we say, let's start all over again. Year 1 and 2 and 3, and the Earth keeps doing this constantly. It doesn't stop, and it's perfect.
And if it was anything different, like you were saying, if it went off that path of orbit, what would really happen?
Yes.
And that they come out with these studies every year about how Earth's orbit is shifting by a very, very minimal change within the eccentricity, very minimal. And they do talk about what if the eccentricity does change for Earth's orbit, what would happen?
Yes. So these are the implications that more research needs to be done, so we can come up with what can we do? Can we move the Earth back to its orbit?
Is that something that's even possible?
Is there a way to, let's say that asteroid hits Earth so hard, it shifts its orbit. What are the implications? So of course, now the good news is they have tools to shift some of the asteroids that might come and hit Earth. Just shift them a little bit. They can change. The trajectory can be different.
And not only within our solar system, what are there other implications with radio reflections for medicinal purposes?
Yes.
Such as radiation or like treating kidney stones,
Mm-hmm. Yes. I think these are the things that I'm pretty sure that some people are working on. They probably ask the same questions. More likely, they have the same questions, and they're working on these things. So hopefully, one day we're ready, just in case. Even these are the things that, like our universe. It's especially if you even look at our galaxy. If you only make it smaller than that, just the planets that are orbiting the sun.
And
if one of them changes its orbit, what are the implications for the other ones?
Exactly. And I think that another cool thing is that these properties of ellipses, they were actually found in the 1600s. And the Paul's Cathedral was actually built in 1672,
No.
which means that they knew how this architectural style could affect how sound traveled within that building in
Yes.
1672,
Wow.
which is a long time ago.
Talking about technology.
Talking about asteroids coming and hitting Earth and hitting us off orbit. And they were talking about all of these properties back in the 1600s.
Wow. Wow,
That's amazing.
incredible. Yeah, yeah. So contrary to we might think now, they were very advanced scientifically. We've made great progress, but even way back then, like the example that you gave, it shows that they really grasp, they have really an understanding of how the ellipses and the eccentricity, how all of these things work, really.
That's amazing.
Yeah.
All right. Is there anything else that we should add?
On mine, I think that would be it.
All right.
Is there anything else you want to add to this?
Nope.
All right.
Let me.
Well, I can say thank you very much for the teamwork effort.